Welcome to DAR Tutors for online and home tuition. Today, we're diving into a fundamental and highly applicable branch of mathematics, graph theory. Specifically, we will be covering transition matrices for graphs, trees, and spanning trees, minimum spanning trees using Kruskal's and Prim's algorithms, and Eulerian graphs. These concepts are not just abstract, they are the bedrock for modeling and solving real-world problems. By the end of this session, you will be proficient in using these tools to tackle various scenarios, from museum floor plans to network design. Let's begin by considering an example involving a museum floor plan, which can be represented by an adjacency matrix. The letters A to F represent 6 distinct areas within the museum. The matrix, which is shown here, tells us if there's a direct connection between any two areas. A1 indicates a direct path exists, while a 0 means there is no direct path. Our first task is to determine if the matrix A is symmetric about the leading diagonal and to explain what this property signifies. Looking at the matrix, we can see it is not symmetric. For example, the entry AC is 0, but the entry CA is 0. A more obvious case is AB, which is 1, but AD is 0. For a matrix to be symmetric, the entry at row I, column J, must equal the entry at row J, column Y for all I and J. Since this is not the case for matrix A, we conclude it is not symmetric. This asymmetry tells us that the paths are one way. For instance, you can walk from area F to area A, as shown by the 1 in row F, column A, but you cannot walk directly from A to F, because the entry in row A, column F is also 1. This means the path between A and F is directed, likely allowing travel in only one specific direction. Let's take a closer look at the A to F example. Row A, column F is 1, and row F, column A is also 1. This means you can travel from A to F, and you can also travel from F to A. So the path is undirected. However, look at A to C, which is 0, but C to F is 1. Since they are not equal, the matrix is not symmetric. In essence, a non-symmetric adjacency matrix indicates a directed graph, where movement between nodes can be restricted to a single direction. Now, let's move on to the next part of the problem. We are asked to draw a graph to represent the museum's floor plan based on the given adjacency matrix. Here we have the graph representation of the museum. The 6 nodes A through F correspond to the areas in the matrix. The arrows, or directed edges, represent the one-way paths. For example, the entry A at 12 equals 1 means there is a path from A to B. So we draw an arrow from A to B. The entry A is 24 equals 1 means there is a path from B to D. So we draw an arrow from B to D and so on. Notice the structure of the graph. Node E has no outgoing edges. This is a crucial observation for the next part. Next, we need to assign roles to the nodes: entrance, shop, and exit. For the exit, we should look for a node that has paths leading into it, but no paths leading out. This makes sense for an exit. In our graph, only node E fits this description. There are arrows pointing to E, but none originate from it. So we identify node E as the exit. The shop is typically a place you visit and leave, so we're looking for a node that is neither an entrance nor an exit. Many nodes fit this. The entrance should be a central hub with paths to many other areas. Node A is a good candidate here. It has paths to B, E, and F. Let's continue with the museum problem. We're told that to reach the dinosaur room, one must pass through exactly 2 other rooms from the entrance. We've identified the entrance as node A, so we need to find the node that is exactly 3 stops away from A. A, room 1, room 2, dinosaur room. To find paths of length 3, we need to calculate the powers of the adjacency matrix. We are specifically asked to calculate A plus A squared and A cubed. Let's first calculate A squared, which is A multiplied by A. A squared gives us the number of paths of length 2 between any 2 nodes. The entry in row I, column J of A squared is the number of ways to go from node I to node J in 2 steps. After performing the multiplication, we get the matrix A squared. For example, the element in row A, column A is 2. This means there are 2 paths of length 2 that start and end at A. Let's check them on our graph: A to B to A and A to F to A. Next, we calculate a cubed by multiplying a squared by a. The resulting matrix a cubed tells us the number of paths of length 3 between any two nodes. The element in row I, column j of a cubed is the number of ways to go from node I to node j in 3 steps. The resulting matrix a cubed tells us the number of paths of length 3 between any two nodes. The element in row I, column j of a cubed is the number of ways to go from node I to node j in 3 steps. Now we can perform the final calculation required, a plus a squared. We add the corresponding elements of matrix A and matrix A squared. This matrix represents the total number of paths of length 1 or 2 between any two nodes. So, for example, a visitor starting at A can reach A in 2 ways, length 1 or 2, B in 2 ways, C in 0 ways, D in 2 ways, and F in 2 ways. We've done the calculations. Now let's use them to find the dinosaur room. Remember, the rule is, from the entrance, one must pass through 2 other rooms to get to the dinosaur room. This means we are looking for a room that is connected to the entrance, A, by a path of length 3. Since a cubed tells us the number of paths of length 3, we look at the row in a cubed corresponding to our entrance, which is A. This is the first row. This row shows the number of ways to get from A to each other room in exactly 3 steps. We see a non-zero number in column E, which corresponds to room E. The entry is 4. This means there are 4 different paths of length, 3 from the entrance A to room E. So, our first conclusion is that the dinosaur room is E. Let's verify. One path is A to B to D to E. This path goes through 2 other rooms, B and D, and is of length 3. Now, let's address the question about comparing A plus A squared and A cubed. The matrix A plus A squared tells us the number of paths of length 1 or 2 from each starting room. The matrix A cubed tells us the number of paths of length 3. By comparing these, one could potentially rule out rooms if a path of the required length, in this case 3, was not present. Now let's shift our focus to transition matrices, which are essential for understanding Markov chains and analyzing movement in weighted, directed graphs. A transition matrix T describes the probabilities of moving from one state, a starting vertex, to another, a finishing vertex. The key difference from an adjacency matrix is that its entries are probabilities, not just zeros and ones. A crucial property of any transition matrix is that the sum of the probabilities in each row must equal 1. This reflects the certainty that the bus, for example, will travel somewhere from its current city. In this specific book's convention, the rows represent the starting vertices and the columns represent the finishing vertices. This means that to find the probability of moving from, say, city A to city B, we look at the entry in row A, column B. The given example matrix T follows this convention. From city A, there's a 0.6 probability of going to B and a 0.4 probability of going to D. Notice that 0.6 plus 0.4 equals 1, satisfying our row sum property. Let's test this with row B. The probabilities are 0.3, 0, 0.2, and 0.5. Summing them up, 0.3 plus 0.2 is 0.5, and 0.5 plus 0.5 is 1. Again, the row sum is 1. This row sum property is a vital check for any transition matrix. Now that we have our transition matrix T, we can use it to predict future states. This involves using powers of T and an initial state vector. Let's say a bus starts in city B. We can represent this initial state as a row vector, where the entry corresponding to B is 1, and all others are 0. The convention is that if we multiply this state vector by the transition matrix, the state vector must be a row matrix and must pre-multiply T. So, to find the state after one stop, which we'll call S1, we calculate S0 times T. Multiplying the state vector 0, 1, 0, 0 by our transition matrix T gives us the vector 0.300205. This resulting vector, S1, tells us the probability of the bus being in each city after one stop. So, from starting in B, there is a 0.3 probability of being in city A, a 0.2 probability of being in city C, and a 0.5 probability of being in city D. For 2 stops, we would calculate S2 equals S0 times T squared. And for n stops, we calculate Sn equals S0 times T to the power of n. For example, The textbook shows that if we calculate t cubed and look at the entry in row B, column D, which is 0.385, it means there is a 0.385 probability that a bus currently in B will be in D 3 stops from now. This is a powerful tool for long-term prediction. Let's apply these concepts to an IB-style problem. A train moves between 3 stations, P, Q, and R, according to these probabilities. Part A asks us to complete the graph by finding the missing probabilities for the edges from P to Q and R to Q. We know that the sum of the probabilities from any node must be 1. From node P, we have one known probability of 0.3 to R. Therefore, the probability to Q must be 1 minus 0.3, which is 0.7. From node R, we have one known probability of 0.4 to P. So the probability to Q must be 1 minus 0.4, which is 0.6. So our completed graph has a probability of 0.7 from P to Q and 0.6 from R to Q. This completes the first part. Next, we need to construct the transition matrix T from this graph. The rows will be the starting stations P, Q, R, and the columns will be the finishing stations P, Q, R. Let's fill in the matrix row by row. For row P, from P, the probability to Q is 0.7 and to R is 0.3. There is no edge to P, so that's 0. For row Q, from Q, the probability to P is 0.7 and to R is 0.4. There's an inconsistency in the question. The textbook says the sum of Q's outgoing edges is 1.1. In a real IB exam, a question like this would be checked for consistency. Let's assume the question meant for Q to be a node with total outgoing probability 1. If the probabilities from Q were 0.7 to P and 0.3 to R, the matrix entry for Q to R would be 0.3. For now, let's proceed with the given values and note the discrepancy. So, our matrix T with the corrected Q to R probability of 0.3 is, from P 0 to P is 0.7 to Q, 0.3 to R. From Q 0.7 to P, 0 to Q, 0.3 to R. From R 0.4 to P, 0.6 to Q, 0 to R. This matrix now correctly sums to 1 for each row. Let's continue with the IB train problem, part C. We need to interpret the value in row 1, column 3 of the matrix T we just constructed. This corresponds to the entry in row P, column R. Looking at our matrix, the value in row 1, column 3 is 0.3. This value represents the probability that a train currently at station P will move to station R in its next stop. In other words, it is the one-step transition probability from P to R. Now for part D. We are given that a train is currently at station P. This gives us our initial state vector, S. The vector 1, 0, 0 correctly shows that there is a 100% chance the train is at P and a 0% chance of being at Q or R. We need to calculate S0 times T cubed. First, let's find T squared by multiplying T by T. Multiplying our T matrix by itself gives us T squared. This matrix contains all the probabilities of transitions occurring in 2 steps. Next, we find T cubed by multiplying T squared by T. Finally, we multiply our initial state S0 by T cubed. Because S0 is 1, 0, 0, multiplying by T cubed simply gives us the first row of T cubed. To interpret this answer, if the train starts at station P, the probability it is at station P after 3 stops is 0.498. The probability it is at station Q is 0.477, and the probability it is at station R is 0.025. We have reached the 10-minute mark. If you find these explanations helpful and would like more personalized support, please consider contacting DAR Tutors. We offer expert tuition in IB A-Level and IGCSE curricula designed to help you achieve your academic goals. Now let's transition to a new topic in graph theory, trees. A tree is a special type of graph with 3 main properties. First, it must be connected, meaning there is a path between any 2 vertices. Second, it must be simple, meaning no loops or multiple edges between the same 2 vertices. And most importantly, it must contain no cycles. This means you cannot start at a vertex and follow edges to return to it without repeating any edges. These examples clearly show what trees look like. You can traverse them from one end to another without ever finding a closed loop. A key result in graph theory states that every connected simple graph has a tree as a subgraph. This is a very useful idea. This leads us to the concept of a spanning tree. A spanning tree of a graph G is a subgraph that is itself a tree and includes every single vertex of the original graph G. So it connects all vertices with the minimum number of edges needed to form a tree structure. Consider the graph shown here. The shaded red subgraph is a spanning tree. It is connected, has no cycles, and includes all 6 vertices from the original graph. It spans the entire graph. There's a critical relationship between the number of vertices, which we'll call n, and the number of edges in any spanning tree. Let's investigate this relationship with a few examples. For the first graph, there are 4 vertices. Its spanning tree has 3 edges. For the second graph, there are 6 vertices, and its spanning tree has 5 edges. For the third graph, there are 8 vertices, and its spanning tree has 7 edges. By observing this pattern, it's clear that the number of edges is always 1 less than the number of vertices. If a graph has n vertices, any spanning tree for that graph will have exactly n1 edges. This property is a hallmark of all trees. A connected graph with n vertices is a tree if and only if it has n1 edges and no cycles. This is a very important theorem to remember. Now, can every graph have a spanning tree? The answer is no. A graph must be connected for a spanning tree to exist. If a graph has 2 or more distinct connected components, it's impossible to connect all vertices with a single tree structure. The spanning tree must touch every vertex. Now we combine these ideas with weighted graphs to arrive at a powerful and practical concept. Minimum spanning trees, or MSTs. Consider this graph representing hiking trails in a national park. The vertices are landmarks and the edge weights are the lengths of the trails in kilometers. The park wants to pave sections of these trails to connect all landmarks for wheelchair access, using the absolute minimum amount of paving. This problem requires us to find a spanning tree, a set of connected trails that covers all landmarks without any unnecessary loops, but with the smallest possible total weight. This is precisely the definition of a minimum spanning tree. A minimum spanning tree for a weighted graph is a subgraph that is a tree, contains all vertices of the graph, and has the smallest possible sum of edge weights. It represents the most efficient way to connect a network. The challenge is finding the MST efficiently for large graphs. For this, we have 2 primary algorithms. First, Kruskal's algorithm, which builds the tree by adding edges of increasing weight, always checking for cycles. Second, Prim's algorithm, which starts with a single vertex and grows the tree outwards by adding the nearest available edge. We will explore both of these in detail. Let's begin with Kruskal's algorithm. The core idea is simple. We sort all the edges by weight and add them to our tree one by one, from lightest to heaviest, making sure that adding an edge doesn't create a cycle. Here's the procedure. Step 1. Start with the shortest available edge. Step 2. Choose the shortest remaining edge that connects 2 previously unconnected components. This step is crucial for avoiding cycles. Step 3. Repeat until you have n1 edges, where n is the number of vertices. Once you have n1 edges and they form no cycles, you've found your minimum spanning tree. Let's work through an example. Here's a graph with 7 vertices. This means our MST will need 7 minus 1, or 6 edges. Step 1 is to list all the edges and their weights in ascending order. The lightest edge is FG, with weight 2. We add it to our MST. The next lightest edges are DE and AC, both with weight 3. We can add both to our tree as they don't connect any existing components or create a cycle. The next lightest is EG, with weight 4. We add it. Next is EF, with weight 5. Adding EF would create a cycle between E, FG, and E, so we reject it. Next is CE, with weight 5. It connects vertex C to the component containing E, F, and G, so we accept it. The next edge is CD, with weight 5. Adding CD would create a cycle CDEC, so we reject it. We now have 5 edges. We need one more. The next lightest edge is AB, with weight 6. It connects component HYK to BE. This doesn't form a cycle. We accept it. We now have 6 edges, so we stop. Our MST has edges FG, DE, AC, EG, CE, and AB. The total weight is the sum of these weights. 2 plus 3 plus 3 plus 4 plus 5 plus 6 equals 23. Now let's examine the second algorithm for finding a minimum spanning tree. Prim's algorithm. The approach is different, but the goal is the same. Prim's algorithm is a greedy algorithm that builds a tree by adding edges one at a time, always choosing the edge that connects an additional vertex to the existing tree with the smallest possible weight. Here's the procedure. Step 1. Start with any arbitrary vertex. The choice does not affect the final weight. Step 2. From that vertex, add the edge with the smallest weight, connecting a new vertex to our growing tree. Step 3. Now consider all vertices that are not yet in the tree and find the one that is closest to any vertex already in the tree. Add that edge and vertex. Step 4. Repeat step 3 until all vertices are included in the tree. Let's apply this to an example. We'll start at vertex A. The edges connected to A are AB, AC, AD, and AF. The shortest of these is AC, with a weight of 12, so we add AC to our tree. Our tree now consists of vertices A and C, connected by edge AC. Now we need to find the nearest unconnected vertex to either A or C. Let's list the available edges, from A to B 27, from A to D 15, from A to F 16, from C to B 6, from C to D 14, from C to E 18. The shortest of all these is CB, with weight 6, so we add CB to our tree. Our tree now consists of A, C, and B. We continue this process. The next nearest edge from our current tree, A, B, C, is CD with weight 14. We add it. From A, B, C, D, the next nearest is DE with weight 7. We add it. From A, B, C, D, E, the next nearest is FG with weight 5. We add it. And finally, the next nearest from A, B, C, D, E, F, G, E is DF with weight 9. We add it. We now have 6 edges, so we stop. The resulting MST has edges AC, CB, CD, DE, FG, and DE. Its total weight is 12 plus 6 plus 14 plus 11 plus 5 plus 9, which equals 57. Notice that both Kruskal's and Prim's algorithms produced an MST with the same total weight as expected. Prim's algorithm can also be performed using an adjacency matrix, which can be very systematic. Let's revisit our example using this matrix method. Here is the adjacency matrix for our graph. The entries represent the weights of the edges. A dash means no direct connection. We'll follow a few simple rules. Step 1. Start by picking any vertex, say E. We delete the row and number the column of our chosen vertex. So, we delete row E and number column E with a 1. Now, in column 1, we find the smallest undeleted entry. That's the 11 in row D, column E. We circle it and make D our new chosen vertex. Step 2 repeats. Delete the row and number the column of our new vertex, D. So, delete row D and number column D with a 2. Now we look for the smallest undeleted entry in any numbered column, E or D. That's the 9 in row F, column D. We circle it and make F our new vertex. We continue this process. The circled entries will be our MST edges. We would then delete row F, number col F with a 3. The next smallest entry is 5, GF. We circle it and choose G. Then delete row G, number col G with a 4. The next smallest is 14, CD. We circle it and choose C. Then delete row C, number col C with a 5. The next smallest is 6, BC. We circle it and choose B. Finally, delete row B, number col B with a 6. The next smallest is 12, AC. We circle it and choose A. All rows are deleted. The circled entries represent the edges of our MST, D11, DF9, GF5, CD14, BC6, and AC12. The sum of their weights is 57, exactly the same result we got visually. This method provides a clear, systematic way to apply Prim's algorithm. Let's move on to our final topic in graph theory, Eulerian graphs. We'll start with a classic historical problem that set the stage for this entire field. The bridges of Königsberg. The town of Königsberg was split by a river. with 7 bridges connecting 2 islands and the 2 riverbanks. The question was, could a person start at one landmass, walk across every single bridge exactly once, and return to their starting point? In 1736, the great mathematician Leonhard Euler proved this was impossible, giving birth to graph theory. We can represent this problem as a graph. The 4 landmasses are our vertices, and the 7 bridges are our edges. We need to find a circuit that traverses every edge exactly once. This is what we call an Eulerian circuit. Euler proved that for such a circuit to exist in a connected graph, every single vertex must have an even degree. The degree of a vertex is simply the number of edges connected to it. For the Königsberg graph, the degrees of all 4 vertices are odd. Since they are not all even, an Eulerian circuit is impossible. This leads us to a general rule for classifying graphs. Based on Euler's work, we can classify graphs as Eulerian, semi-Eulerian, or neither by simply looking at the degrees of their vertices. Let's formalize this. A path that traverses every edge exactly once is called an Eulerian trail. If this trail starts and ends at the same vertex, it is an Eulerian circuit. The classification depends on the number of odd-degree vertices in a connected graph. First, if a connected graph has no vertices with an odd degree, meaning all vertices have even degrees, then it is an Eulerian graph. This means an Eulerian circuit exists, and you can start at any vertex, traverse every edge, and finish back where you started. Second, if a connected graph has exactly 2 vertices with an odd degree, and all others have even degrees, then it is a semi-Eulerian graph. In this case, an Eulerian circuit is not possible, but an Eulerian trail exists. This trail must start at one of the odd-degree vertices and will end at the other. Third, if a connected graph has more than 2 odd-degree vertices, then it is neither Eulerian nor semi-Eulerian. No Eulerian trail or circuit can exist in this graph. The Königsberg bridge graph was an example of this. Let's work through an example to see how to apply these rules. Consider the graph shown here. We need to determine if it is semi-Eulerian, and if so, find a trail. The first step is to calculate the degree of each vertex. Looking at the graph, the degree of A is 2, the degree of B is 4, the degree of C is 2, the degree of D is 2, and the degree of E is 4. No, wait, let's recount. A has degree 2. B has edges to A, C, D, and E, so degree 4. C has edges to B and D, so degree 2. D has edges to B, C, and E, so degree 3. E has edges to A, B, and D, so degree 3. So we have exactly 2 vertices with odd degrees, D and E. This means the graph is semi-Eulerian. An Eulerian trail exists, and it must start at one of these odd vertices and end at the other. Let's try to find one starting at D. A possible trail is D to B, then B to C, then C to D, returning to D momentarily, then D to E, then E to B, and finally B to A. Let's trace that on the graph. D to B, B to C, C to D, D to E, E to B, and B to A. This trail uses every edge exactly once and ends at A. But A is not E, which is our other odd-degree vertex. Let's try another path. The textbook offers D to B, B to C, C to D, then D to E, E to A, and A to B. Let's re-examine the degrees. A has edges to B and E, so DG, A to our 2. B has edges to A, C, D, E, so DG, B, Sashir 4. C has edges to B and D, so DG, C, 2. D has edges to B, C, and E, so DEG, D, 3. E has edges to A, B, and D, so DEG, E, 3. Yes, degrees are AX2, B4, C2, D3, E3. The odd degrees are D and E. A trail must start at D and end at E. So, the textbook's example trail is incorrect for its own graph. An Eulerian trail must start and end at the odd degree vertices D and E. A valid trail is D to C, C to B, B to A to E, E to D. Oops, that's a cycle D to E to A to B to D, and then D to B, and finally B to E. So DC, BA, E, DBE. This starts at D and ends at E. That's a valid Eulerian trail for this graph. This illustrates how important it is to carefully calculate degrees. Let's continue with the same example and look at parts B and C. Our goal is to manipulate the graph to make it Eulerian and find a circuit. Part B asks for an Eulerian trail. Based on our corrected degree analysis, the trail must start at D and end at E. We found a valid one in the last scene. We determined that the odd degree vertices are D and E. An Eulerian trail must start at one of these and end at the other. One such trail is D to C, then C to B, then B to A, then A to E, and finally E to D. Wait, I made a mistake tracing that one. Let's find one that does not repeat edges. Let's try this one. Start at D, go to B, then B to E, then E to A, then A to B, then B to C, and finally C to D. Wait, this goes D, B, E, A, B, C, D. I've used edge DB twice. The key is to traverse each edge exactly once. The textbook suggests this sequence. D to C, then C to B, then B to E, then E to A. We've now used 4 edges, then A to B, which completes the tour of the triangle AB. And finally, E back to D. So DC, BE, AB, D. This uses edges DC, CB, BE, EA, AB, and BD. This is an Eulerian trail. It starts at D and ends at D, which contradicts my earlier statement about it having to end at E. This is why it's so important to verify. Let's check the degrees again. This is getting confusing. AB, AE, BC, BD, BE, CD, DED. AAE, DGE2, BDBA, BC, BDEB, DGE4. EEDG2, DDDCDED3, EEAEBD DG3. Yes, D and E are the odd ones. The trail must start at one and end at the other. The text trail D to C is B to E, A, B to D ends at D. The trace seems to suggest DCBEABD. This uses AB twice and BD twice. This example in the textbook is actually problematic. Let's ignore their specific trail and just focus on the principle. Start at D, end at E. Let's move to part C, which is less ambiguous. We want to add an edge to make the graph Eulerian. Remember, to be Eulerian, all vertices must have an even degree. Currently, vertices D and E have odd degrees, 3. The other vertices, A, B, C, have even degrees, 2, 4, 2. If we add an edge connecting D and E, we will increase the degree of D by 1, making it even 3 plus 1, 4. We also increase the degree of E by 1, making it even 3 plus 1, 4. Now all vertices have even degrees. The graph is Eulerian. With the new edge DE, we can find an Eulerian circuit starting at any vertex. Let's try starting at D and including our new edge DE. A possible circuit is D to E, the new edge, then E to A to B, B to C, C to D. We've now completed a circuit and used all edges in the A, B, C, D, E pentagon. From D, we go to B, then B to E. We've now used all edges and returned to D. So the circuit is D, E to E, B to C, D, B, E, D. Let's work through another IB-style Eulerian graph problem. This graph is from a zoo map. A visitor wants to tour the zoo, starting at the entrance E, traversing every track exactly once, and ending back at E. Is this possible? The question asks for an Eulerian circuit. To check if one exists, we must first calculate the degree of every vertex and identify the odd ones. By tracing the edges, we find the degrees for each vertex. For example, E has edges to D, F, G. That's a degree of 3. D has edges to B, C, E, F. That's a degree of 4. We continue this for all vertices. After calculating all degrees, we find that vertices A, B, C, F, and G all have a degree of 4, which is even. However, vertices D, E, H, I, and J all have a degree of 3, which is odd. This graph has 5 vertices of odd degree. Since the graph has more than 2 odd-degree vertices, it is neither Eulerian nor semi-Eulerian. Therefore, it is impossible for the visitor to take such a tour. This directly answers part A. Part B asks what track could be built to make such a tour possible. Adding a track between any two of the odd degree vertices will fix 2 degrees, making them even. We need to reduce the number of odd degree vertices from 5 to 0. This requires adding multiple edges or using a more advanced technique. A simpler way is to connect all the odd degree vertices together. This forms a clique on the odd vertices. However, the question seems to imply adding a single track. If we add 1 track, we can reduce the number of odd vertices by 2. This is still not enough. Let's reread the question carefully. Name a track that could be built to make such a tour possible. This could be interpreted as adding multiple tracks. If we wanted an Eulerian circuit, all 5 odd degrees must become even. This would require adding multiple tracks. If we just wanted an Eulerian trail, we'd need to get down to exactly 2 odd degree vertices. This would require adding an edge between 2 odd vertices. Given the wording, a common approach for making it possible in such a problem is to connect all odd degree vertices. This is called Eulerianizing the graph. If we connect all 5 odd vertices to each other, we form a K5 graph on those 5 vertices. The degree of each of these 5 vertices would increase by 4, making their new degree 7, which is still odd. This doesn't seem to work. This suggests that the question is ill-posed as it is. Let's assume there is a typo and there are only 2 odd degree vertices. For example, if H, I, and J had different degrees and we could reduce it to just D and E being odd. In that case, adding a track between D and E would work. But based on the degrees I calculated, this is not the case. Let's summarize the key takeaways from today's session. We started with transition matrices, which model probabilities of movement in weighted directed graphs. Key properties are that rows sum to 1, and we use S0 times t to the n to find future states. Then we introduced trees, which are connected, simple graphs with no cycles. We learned about spanning trees, which connect all vertices of a graph, and the crucial relationship that a spanning tree for n vertices always has n1 edges. This led us to minimum spanning trees, or MSTs, the most efficient way to connect a network. We discussed 2 algorithms for finding them. Kruskal's, which builds the tree edge by choosing the smallest weight edges that don't form a cycle, and Prim's, which grows the tree vertex by adding the nearest available edge. Finally, we covered Eulerian graphs, which allow for a circuit or trail that visits every edge exactly once. The key to classifying them is to count the number of odd degree vertices: 0 for an Eulerian graph, circuit, 2 for a semi-Eulerian graph, trail, and more than 2 for neither. These concepts are fundamental in various fields like computer science, logistics, and network design. A strong understanding will be invaluable for your IB studies and beyond. Thank you for watching. Now, for your practice and review, here are 5 IB-style questions. I recommend pausing the video after each question, attempting to solve it yourself, and then watching the worked solution to check your work and reinforce your understanding. Let's begin. Here is our first practice question. A train travels between cities A, B, and C. The probabilities of moving between them are given in this directed weighted graph. Your task is to construct the transition matrix T for this system and find the probability that a train starting at A is at C after 2 journeys. Pause the video here and attempt this question on your own. Remember to first construct the transition matrix and then use its powers. Welcome back. Let's work through the solution for practice question 1. The first step is to construct the transition matrix T. We'll use the convention that rows are starting points and columns are finishing points. From A, there is a 0.7 probability to B and a 0.3 probability to C. From B, there is a 0.6 probability to C and a 0.4 probability back to A. From C, there is a 0.5 probability to A and a 0.5 probability to B. This gives us our matrix T. Next, we need the initial state vector, S0. The train starts at A, so S0 is 1 near 0. We need to find the probability of being at C after 2 journeys, which is S0 times T squared. So we must first calculate T squared. Multiplying T by itself gives us T squared. For example, the element in row A, column A, is 0.0 plus 0.7 equals 0.4 plus 0.3 plus 0 to 0.5, which is 0.28 plus 0.15 equals 0.43. Finally, we calculate the state after two steps, S2, by multiplying S0 by t squared. This gives us 0.38 to 0.35.27. The third entry, 0.27, is the probability of being at sea, so the final answer is 0.27. So the probability that the train is at City C after two journeys is 0.27. If you got this right, well done. Here's our second practice question. Find the minimum spanning tree for the graph shown here using Kruskal's algorithm. You need to state the total weight of the tree. Pause the video and work through Kruskal's algorithm. Remember to list edges by weight and check for cycles. Let's review the solution for practice question 2. We'll use Kruskal's algorithm to find the MST. First, the graph has 5 vertices. Therefore, our MST must have N1, or 4 edges. Next, we list all the edges and their weights in ascending order. The smallest weight is 20 for the edge DE. We add it to our MST. The next smallest is 25 for BC. We add it. The next is 30 for BD. Adding BD would create a cycle BCDB, so we must reject it. The next edge is CD, with weight 40. This does not create a cycle with our existing edges, so we add it. We now have 3 edges, DE, BC, CD. We need one more. The next available edge is AC, with weight 50. Adding AC does not create a cycle, so we accept it. We now have 4 edges, so we stop. The edges in our minimum spanning tree are DE, BC, CD, and AC. To find the total weight, we sum these weights, 20 plus 25 plus 40 plus phi, which gives us 135. That is the minimum weight to connect these 5 vertices. Here is our third practice question. This graph represents a network of pipelines with the weights representing costs. Your task is to find a minimum spanning tree using Prim's algorithm and state its total weight. Pause the video here. Remember, you can start at any vertex. Let's try starting at vertex A. Let's review the solution for practice question 3. We'll use Prim's algorithm starting at vertex A. We start our tree with vertex A. The edges connected to A are AC, weight 12, AD, weight 15, and AB, weight to 7. The shortest of these is AC, so we add edge AC to our tree. Our tree now includes vertices A and C. We look for the shortest edge from either A or C to an unconnected vertex. The options are AB, 27, AD, 15, CD, 14, CB, 6, CE, 18. The shortest is CB with weight 6. We add CB to our tree. The tree now includes A, B, and C. The shortest edge from any of these to an unconnected vertex is CD with weight 14. We add it. The tree now includes A, B, C, and D. The shortest edge from this set to an unconnected vertex is DE with weight 11. We add it. The tree now includes A, B, C, D, and E. The shortest edge to an unconnected vertex is FG with weight 5. We add it. The tree now has all 6 vertices and 5 edges. We stop. Our minimum spanning tree is composed of the edges AC, CB, CD, DE, and FG. Summing their costs gives a total weight of 12 plus 6 plus 14 plus 11 plus 5, which equals 48. Notice that this is a different set of edges from the one found by the textbook example for this graph, but the total weight is indeed smaller, showing there can be multiple valid MSTs, though the weight is always unique. Here's our fourth practice question. A mouse travels through a maze with junctions W, X, Y, and Z. We need to construct a transition matrix assuming the mouse chooses a random path at each junction. This problem has 2 key parts. First, identifying the connections and degrees, and second, understanding the phrase chooses his next tunnel at random. At each junction, the mouse has several tunnels to choose from. At random means each available tunnel is equally likely, so the probability of taking any single tunnel is 1 divided by the degree of the vertex. Pause the video and construct the matrix.